Have you ever wondered what causes the rainbow colors of soap bubbles or oil slicks? Click the oil slick button to observe this everyday phenomenon. The colors are due to interference of light reflected from surfaces of soap bubbles or oil slicks. These phenomena are due to interference in thin films. Introduction to interference in air wedge and thin film. In this lesson, when light is incident on a transparent medium such as glass, part of the light is reflected on the glass surface. Reflection at an interface may cause a phase change, depending on the refractive indices of the media. Click the Air to Glass button to observe the reflected wave. Do you observe any phase change in the reflected wave? Answer: yes. The reflected wave undergoes a phase change of pi radians, which is equivalent to a change in the optical path of half a wavelength. Click the Glass to Air button to observe the reflected wave. Do you observe any phase change in the reflected wave? Answer: no, there is no phase change in the reflected wave. A phase change of pi radians occurs when light is reflected from a denser medium. When light is reflected from a less dense medium, there is no phase change. Let us compare the motion of light waves through a medium and in vacuum. A. Count the number of wavelengths in the medium of distance d and in the distance nd in vacuum. B. Compare their wavelengths. Answer: A. There are 5 complete wavelengths in both. B. The wavelength of light in the medium is smaller than that in vacuum. If light travels a geometrical distance d in a medium of refractive index n, then in the same time it would travel a distance nd in vacuum. The optical path length for a distance d in the medium is nd. Click the Next button. When light travels in a medium, its wavelength is shorter than in vacuum, whereas its frequency remains unchanged. Click the Relationship button to observe how the wavelength of light in a medium lambda is related to its wavelength in vacuum lambda naught. Summary: when light is reflected from a denser medium, it undergoes a phase change of pi radians, which is equivalent to a change in the optical path of half a wavelength. If light travels a geometrical distance d in a medium of refractive index n, then in the same time it would travel a distance nd in vacuum. The optical path length for a distance d in the medium is nd. Monochromatic light of wavelength lambda is incident on a uniform thin film of refractive index n. Click the Play button to observe a ray at a small angle of incidence being reflected at the film. The incident ray is partly reflected by the upper surface of the film as ray 1 and by the lower surface as ray 2. Ray 2 has to traverse an extra optical path of n pq plus qr. Click the 10 degrees button followed by the 5 degrees button so that the incident ray is nearly normal to the film. What is the extra optical path of ray 2 as compared to ray 1 in terms of the thickness T of the film when the incident ray is nearly normal to the film? Answer: the extra optical path is almost equal to 2nt. Since ray 1 is reflected from a denser medium at point P, its optical path increases by lambda over 2. Therefore, the optical path difference between ray 1 and ray 2 is 2nt minus lambda over 2. Click the Condition for Constructive Interference button to see the equation for constructive interference. Click the Condition for Destructive Interference button to see the equation for destructive interference. Non-reflective coatings are used in spectacles, optical instruments, and surfaces of solar cells so that more light is transmitted. The glass surface is coated with a thin layer of transparent material which has a refractive index less than that of glass. Click the Incident Ray button to observe the reflection of light from the upper and lower surface of the coating. What is the phase change of the light reflected? A at P and B at Q. Answer: A. On reflection at P, there is a phase change of pi radians. B. Similarly at Q, there is a phase change of pi radians which is equivalent to an optical path of half a wavelength. For the glass surface to be non-reflective, there should be destructive interference between the reflected rays 1 and 2. Click on the Condition button to see the condition for destructive interference. What is the minimum thickness of the transparent material for destructive interference to occur? Click the Minimum Thickness button. A lens of refractive index 1.60 is made non-reflective by coating its surface with a thin film of magnesium fluoride of refractive index 1.38. A. Calculate the minimum thickness of the film for the lens to be non-reflective to light of wavelength 565 nanometers in air. B. Determine whether a film of thickness of 614.4 nanometers make the lens non-reflective for the wavelength 565 nanometers in air. Click the Part A button and then the Part B button. Glass windows are sometimes coated with a thin film of transparent material to minimize the transmission of light. This is possible if the thickness of the film is such that constructive interference occurs for the reflected light. Summary: for nearly normal incident light at a thin film, constructive interference 2nt equals m minus half lambda, where m equals 1, 2, 3, etc. Destructive interference 2nt equals m lambda, where m equals 0, 1, 2, 3, etc. The minimum thickness for a non-reflective coating is T equals lambda over 4n. Monochromatic light of wavelength lambda is incident at an angle I to a thin film of refractive index n and thickness T. Click the 1 button, the 2 button and the 3 button to see the derivation of conditions for constructive and destructive interference. Summary. For non-normal incident light, constructive interference 2nt cos r minus lambda over 2 equals m lambda, where m equals 0, 1, 2, etc. Destructive interference 2nt cos r minus lambda over 2 equals m plus half lambda, where m equals 0, 1, 2, etc.